this method, this Lagrange, so recording has started, and we'll close this to have a bigger, okay. So, extremization of some quantity in presence of conditions or constants. So, this will apply to the Hamilton's principle. For with the non-holonomic, with non-holonomic constraints. So this is the whole approach, and we'll quickly. So if you in what is Hamilton's principle, we have some action. The action was some initial time to final time, line integral of the Lagrangian. This is action. So this has to be extremized. So this has to be extremized to get the equation of motion. That we know. Now we have non-holonomic constant, which other day I show you how to write. How to write those equations. It is LK of the delta of QK sum over K. L I took for many such conditions as 0. This you know how you get this. If in general non-holonomic constant will be, let me explain once more. It will be ALK delta QK plus ALT delta T. But we consider the variation of the path, with some real with the paths with virtual displacement. That means we put some force or external force such that there will be only virtual displacement, which balance those constant forces. So virtual displacement. We will see the meaning of this Lagrange multipliers in that sense, virtual displacements. So if we consider virtual displacement, then delta T should be 0. So you have left with this constant. Okay. Now we'll use Lagrange multipliers method, variation of this and variation of this with the Lagrange multipliers lambda, and then we'll get the equation of motion. Okay. So this variation of the action, from the variation of action, we know you get T1, T initial to T final, and then dt. This we have already done when we discuss dt of del L del Qi dot, and this is del Qi. This is the variation. I'm not saying this is equal to 0, but this is coming from the action. Then we have to use sum over lambda L with L, and then sum over K A L K delta QK. And its variation along the path has to be taken, so it will also be inside this integration. Okay. So now what are the lambda L's? Lambda L's are Lagrange multipliers. Lagrange multipliers. So you remember the Lagrange multipliers when we consider delta F plus lambda delta G1 equal to 0. So this is now this variation for extremum condition has to be 0. And we have many such conditions, so that is why we wrote delta f sum over lambda L, then dg dgl. Okay, you have many equal to 0. So exactly, I think this should be clear from the last lecture. Okay, so this sum is 1 to n. You have n coordinates. This sum there will be this there will be also summation. I think the variation will have some sum, right? This variation will have a summation over I equal to 1 to n. This is k equal to 1 to n. So if this summation from this term and this term, if we take together, then we'll have t initial to t final, then dt. Then we have sum over, let us write I equal to 1 to n, del L del qi minus ddt of del L del qi dot plus sum over lambda plus sum over lambda okay, plus sum over lambda, and then lambda L, and this sum I have taken, so a L I, okay, and then delta Q I is outside. This summation k I replaced by I, so it will be delta Qi, so I have written in the, and this is equal to 0. Now problem is that this Qi for all n values are not independent, right? So when you consider this, I explained in the case of this that all x, y, z are not independent, but there is, we put additional lambda L. So just to remind you that that we have L equal to 1 to m and I equal to 1 to n. This is the number of total coordinates. This is the number of constraints. So m must be less than n, right? Number of constants should be less than this. Okay. So now these all are not independent, but because there are m number of constraints, so there will be n minus m coordinates will be independent, and there are or alternatively you can think of that you have now introduced m number of lambda 1 to 1, lambda 2 to lambda m. So then we can think of that q's are independent, and we can put this condition as in the case of Lagrange multipliers. Okay, so and then we can get equation of motion. Okay, so okay, so you can put let us consider just a moment. Let us consider that just a moment. I'll just want to see. Okay, so by introducing the lambda, so now your number of variables are n plus m, okay, because m number of lambdas, qi are n number, and then there are lambda. So total number of variables like this, and you have equation. In equation you have delta a l q delta q, this equal to 0 for sum over L. So this m number of equation here and n number of, so total n plus m equation, n plus m variable, right? So now you can think of these q's I are independent. So you q's I are independent if you, because the constraint things are carried by lambda. Okay, so you can put then this inside the integration quantity, this quantity equal to 0. Okay, so let me use a different pen. So you can get the equation of motion sum over and no, the sum is outside. So this you can write the equation of motion del L del Qi minus ddt of del L del Qi dot plus sum over L. When I consider example, it will be clear. A L I equal to 0. So this will be your equation of motion. But remember, here you have I equal to 1 to n. So among these, m equation should be used to eliminate lambda. Okay, so basically you should know that if there is a constraint given, but this can be equally valid for the holonomic constant also. We'll consider some example of holonomic constants, and you'll find that how to find equation of motion using directly from this equation. Holonomic case, you can do alternative way, right? You can just eliminate those variable, like in the case of pendulum. We xy variable, then we reduced it to a theta variable or angle of oscillation, and do it. On the other hand, in this case, you can do it by using this method. But you have to remember that m of these equations should be used to eliminate lambda. Those are unknown parameters I introduced by hand for my mathematical purpose, and we have to eliminate those. Those has no role. So, and also you have to consider the constant equation. Constant equation, you remember, k equal to 1 to n a l k delta q k plus a l t delta t equal to 0. This is the constant equation. So this equation together will be considered, and then you will have n plus m number of equations, among which lambda can be determined, and you have exact number of variables, exact number of equation. Okay. Okay, so this is all about the theory. Now we consider example such that it will be clear. But before that, let me tell you some physical meaning of this Lagrange multipliers. So physical, and when we consider examples, we'll see these physical meanings. Okay. Okay. So physical meaning is that suppose we apply some external force to compensate the constraints, such that the system remains unchanged. So we'll apply some, suppose we are imagining the situation. We are applying some external force, and then you can think of that this that external force compensate this. So this is also clear from the equation of motion. So if you don't have the uh, mm, if you don't have the constraints, non-holonomic constant, then we have seen that our equation of motion, if you recall, del L del T del Qi dot minus del L del Qi equal to the generalized force Qi. So in that format, if you write this equation, if you write this equation exactly in this format, so what will happen? I can write. Let me use red. Then ddt of del L del Qi dot minus del L del Qi equal to sum over, see, this sum over lambda L because if I take this in the right side, it will be minus, but I have changed the sign of this two term. Not I have changed the sign, so this will be there. So this quantity the which has the Lagrange multipliers is now comparing to the generalized force. So we can think of the situation that we applied external force which will compensate the forces of constraints. Okay, and Lagrange multipliers is play that role of that force you are applying to the system. The role of the force, external force, which we apply to compensate the constant force. Okay, so this is the physical meaning, but we'll see with an example. So let us consider an example. And we'll consider, to understand, we'll consider only the holonomic cases. Example of holonomic cases. Suppose a particle moves on a circle in 2 dimension. The particle example. Moves on a circle. So this means L can be written half m x dot square plus y dot square. It is a horizontal circle, so no potential energy. Okay, horizontal plane. And then constant equation x square plus y square equal to s square. Okay, now this situation will deal with the new formalism. Okay, so first I'll write this constant equation in that form. So if I differentiate, it will be x dot plus y dot equal to 0, right? So if I write this as a x delta x plus y delta y type of 0, right? So you will find my a x is x, a y is y. Compare that. A L is 1, so I am removing only one constant. So L k and delta q k equal to 0, this sum. So k equal to x, so a x delta x plus a y delta y equal to 0 is coming from this this condition. Only one constant, so I didn't write any L. If you have more than one, you have to write. So this is the equation. So I compare with this, so I can find my ax and ay, because ax and ay you have to calculate this. So first you calculate the equation of motion. So equation of motion for x component. Okay. So equation motion for x component, what you will do? So first you will look at this. So this ddt of del L del x dot. So del L del x dot will be mx dot, then ddt will be mx double dot. Okay, so this term, there is no such term, and then equal to lambda L. L, there is no summation, L is only 1, so only 1 lambda, so it will be lambda 1, or you can write lambda also, times a I is now x, so it will be Ax. Similarly, y component equation will be y my double dot will be again lambda 1 and ay. But ay is and ax is this. So this you can write this equation. This equation is mx double dot is lambda 1 ax x and my double dot is lambda 1 y. Also remember, you have to use this equation also, the constant equation. So this equation only will not give you the solution, because you have two x, y and lambda, three unknown variable, two equations. So you will not get a solution. So you have to use the constant equation. Constant equation is x dot plus y dot equal to 0. So these three equations will give you the solution for this. So let us see what is the nature of this lambda. Okay. So let us see. So here you have to do little bit of mathematics. So let me differentiate this. So x double dot, and there will be y double dot, but here there will be some x dot square, and here you will have y dot square equal to 0, right? So x double dot plus y double dot equal to minus, this is x dot square plus y dot square, so this is v square, right? Minus v square. Now x double dot y double dot I can substitute from here. So let us see how, if I substitute x double dot from here to here, so x double dot will be lambda 1 by m, then x, so it will be x square. Y double dot, if you substitute from here, so it is lambda 1 by m y square, right, equal to v square. So what will be my lambda 1 then? Lambda 1 by m, you take common, x square plus s square is nothing but s square, x square plus y square is s square equal to v square. So lambda 1 will be m minus m v square by s square. So lambda 1 is nothing but or is proportional to the m v square by a, which is centripetal force. So in this situation, we find that what is the role of lambda? Lambda is like a fictitious or imaginary centripetal force on the system, and we can get it. This is a known solution. This solution is a holonomic case, and you can get a solution directly other method also. But to learn this method, I solve this by this method. Okay. Any question here? Is that okay? So similarly, you can solve many other problems with constraints by using this method. For example, generally in exam we ask this student avoid, I don't know, maybe they don't understand much about this, but student avoid. But in exam we generally ask the question that you have a constant and write the equation of motion. So suppose I have a constant, a particle moves in three dimensional particle moves on the surface of a sphere. Or maybe surface of an ellipsoid. Let me write, so x square plus y square b square, let me write, and z square by c square equal to 1. So this is the ellipsoid equation, and particle moves in three-dimensional particle. So first you have to write the constant equation, then you have to write the Lagrangian. Now this is a 3-dimension. Whenever you have a 3-dimension, there will be some potential energy, because any one of the dimension will be vertical. So let us assume the z dimension is vertical. So any 3-dimensional problem, you have to assume one dimension is vertical, and then so Lagrangian kinetic energy will be half m x dot square plus y dot square plus z dot square, and potential energy mgz. So this will be my Lagrangian, and this Lagrangian is constrained to move on this x square plus a square plus y square plus b square plus z square plus c square equal to 1. So you have to find equation of motion. So first you write the constant equation in that form x. So this will be x dot again, y dot again plus z dot equal to 0. I differentiate. So 2 no 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 there will be a, there will be b, there will be c. Okay, equal to 0. ABC will be there because if I differentiate 2, 2 can get cancelled, right hand side is 0. This. So this also you can write that you can find that your AX then is x by A, your AY is y by B, AZ equal to Z by C. And then you can substitute back to your this equation, and this equation, and you will get your so only thing that you have to, so you have to find 3 equation x y z. Okay, and there will be one lambda. You can understand there will be one lambda. Similarly, I can say that okay, this particle moves on the surface of a sphere, ellipsoid, and also subjected to the condition x plus y plus z equal to c. C or maybe D. C is already. So there are 2 constants. So in this constant, if you make a differentiate, so it will be x dot plus y dot plus z dot equal to 0. So in this case, so now in this case, you have a1x, a1y, a1z equal to this. Now a2x will be 1, a2y will be 1, and a3y will be also 1 from this equation. Okay, so x equation, now I can write my x equation, x equation, go back to this equation. So first del L del x dot and ddt. So x dot, if I differentiate, so it will be mx double dot, first term. Then there is no x term, so it will be 0. Second term del L del x, so it will be minus 0 and plus, then you will have a1x lambda 1 plus a2x lambda 2, right? So your equation will be mx double dot plus a1x is how much? X by a lambda 1 plus a2x is 1, so lambda 2 equal to 0. Similarly,
Sir,
y equation,
sir, x by a square 1, x by a square,
yeah,
y
yeah,
by b square.
yeah, sure. This is square. A square and lambda 2 equal to 0. Similarly, y equation will be y by b square lambda 1 plus lambda 2 equal to 0. But z equation will be little bit different because z, there is a potential energy. So when this was 0, but here it will be mg, okay, minus mg, and then minus plus, no? In the Lagrangian, there will be minus, and there will be minus in the formula. Minus plus. This minus in the Lagrangian also it has minus. So it will have mg plus then z by c square lambda 1 plus lambda 2 equal to 0. So these are the 3 equations, and there are 2 lambdas which you have to eliminate. Then only and there are 2, so 5 equation. In fact, 5 equation means this 3, this is 4, and this is 5. So this 5 equations, and from 5 equation 2 of them are to use will be eliminate lambda, and then 3 equation 3 variable x y z. Okay. Okay, so I think you know how to calculate this. I'll consider one more example maybe. This is of course I'll not do the full calculation, but you can do yourself. Suppose I have a inclined plane, and there is a hoop, this circular hoop, which is rolling this. So this length is say L, and its present position is suppose x, and this angle is say phi. Then you have to find the velocity of the hoof at the bottom. Find velocity. And this it has some radius a. Okay. So first thing you have to write the Lagrangian constant equation. Constant equation, I said it's only rolling, so it will be a theta dot will be x dot. Okay, velocity. This is my x direction. This direction I consider as my x direction. So this will be the constant because of this v equal to a omega. So this will be your constant equation, which you can write as a mm, uh, x dot. So delta x plus a delta theta equal to 0. So ax will be 1, sorry, minus, that will be minus. This will go to that. So a theta will be minus a. Okay, but Lagrangian, so this is the constant. So constant you have to handle like this format, and then you have to write Lagrangian. Kinetic energy will be see if the m is the capital M is the mass of the hoop, so m x dot square for the linear motion, and then rotational kinetic energy half m s square theta dot square. Okay. And potential energy at any time it is at this height will be, if this is the this distance, this will be from, this is x distance from this is 0 distance, so this is x distance, so remaining length is L minus x, so this height will be L minus x sine phi, right? This opposite to that, so sine phi. So potential energy will be minus m g h will be L minus x sine phi. Phi is constant here, phi is fixed, this is not a variable, constant. So this is your not kinetic energy minus potential energy, so this is your Lagrangian, this is constant equation. So you now I leave it for you. So find equation of motion, eliminate lambda, and find the velocity, and solve the equation to find the velocity. So this I am not doing, because if I do everything, you'll this is of course given in many books. Okay, so this is all about that what we wanted to discuss about non-holonomic and kind of things. So we'll switch the to other topic. If you have any question, this is best time to ask the question. And the answer, I think you'll get V equal to, I think this GL sine phi. This answer you should able to uh, get for this problem. Okay, apparently it seems you don't have any questions. So let me, the last chapter I am going to start maybe is that two body central force problem. I hope the Lagrangian, Poisson bracket, canonical transformations, etc. Are mole oscillation. These I am not touching at all, and I am expecting that Dr. Krista will cover this. If you have any doubts, difficulties, even from his section, you can always ask me, or any topic you want. Then I'll talk to Krista and we can discuss that also. But it is understandable that I'll now finish the two body central force problem, and that will complete your syllabus.
Sir, Krista sir was saying that central force problem will be taught by both the teachers.
Okay, I'll talk to him, but that was not the understanding. But he has finished the canonical transformation. He has finished the Poisson bracket.
Sir, last class was based upon Poisson bracket only, but not yet finished, I think.
Okay, so then he has to teach the canonical transformation, right? Canonical transformation was not taught.
No, he has taught that.
Oh,
Like that.
no, but Poisson bracket is supposed to be taught before canonical transformation. How otherwise? How canonical transformation? Anyway, I'll talk to him. So if you want to teach this part also, this toward the central force problem, I don't have a problem of that. So we can review many other things, but I'll have a chat with Krista and I'll tell. But anyhow, today we have still 20 minutes time, so we can start the two body central force problem, and so he said it will be taught by both teacher, but that will be misleading, no? But
Yes, sir, he just asked that whether you have started teaching this central force problem. So we told no, not yet. So he told that, okay, let me finish this one and then we have planned to teach
okay,
that.
okay, 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 okay. So then that makes sense. Yeah, that makes sense. So he thought that I'm not able to cover, so he may. Okay. But initially, when we divide the syllabus, it was the plan. But then I am a bit surprised because, for example, Hamiltonian, there are many things. Hamiltonian, then constructing Hamiltonian, particularly for charge particle. This is very, very important. This Hamiltonian you are supposed to get. P minus Q A by C. This Q is charge. So let me write capital Q by C whole square, uh, 2m plus Q phi. This no, this is Q and phi. So this is vector potential and scalar potential. This Hamiltonian, particularly for hydrogen atom and any system. So this you should know. Also how this Hamiltonian changes. Okay, for hydrogen atom, then first you write Hamiltonian for hydrogen atom, then this is the electric and magnetic field, and solution for different configurations. So that, but most important thing which I am sure he has not done is that from this Hamiltonian you get equation of motion. That is this q dot equal to del h del p, and p dot minus will be del h del q. This equation of motion, find this equation of motion from this Hamiltonian, and then this equation motion will give you Lagrange force law. Lagrange force law, that F equal to q e plus v cross b by c. So you should able to derive this. First you write equation of motion using this, then you convert your a phi to your E and B, then you should get this equation. Similarly for the Lagrangian also, in the case of Lagrangian of charged particle, half m x dot square plus y dot square plus z dot square, and then minus q phi plus q by c v dot or x dot ax plus y dot ay plus z dot az. This is the Lagrangian. Find the Euler-Lagrangian equation and convert a phi to e phi, eb, a phi to eb, then you will get Lorentz force. This without doing that, is this not complete? I have not done this for my Lagrangian part, of course, but I was supposed to ask you in the assignment, so that is why I have not done. So you have to submit one assignment before 30th November. Which assignment, how to submit, I'll tell you. Not everybody has to solve those 55 or 60 questions, but you have to solve at least 5-6 problems individually, and I'll try to give you different problem almost for different students, such that you can submit your problems. So I'll break into small group, 10 or 12 groups, all the students, and then I'll prepare 12 problem set, each having 5 or 6 problems, and then you have to solve those problems, and you have to submit for your sessional grading. Copies, I don't know, I have not checked your copies yet. I'll check your copies, and everything will be finalized your out of 30 marks before November or before your exam starts. So this is that. Okay, and then I'll just tell you, I'm telling you such that you can ask Dr. Kista to teach those also. Then in the Poinsot bracket, what you have to by definition. So definition, properties, particularly two properties are very important. One is that Jacobi identity. Of Poisson bracket. And the second properties is that if you have a second properties is that if there are two constant of motion or two constant, let me this is also a problem I asked in exam or problem sheet. Two constant of motion, two constant of motion, then their Poisson bracket also will be a constant. Suppose A is a constant of motion, that means dA dt equal to 0, dB dt equal to 0. They are constant of motion. That means constant of motion means you know del A del T plus Poisson bracket with A with the Hamiltonian equal to 0. Similarly for B. Then this property says that del T of Poisson bracket between A and B also will be constant of motion. So we have two constant of motion, then their Poisson bracket is also constant of motion. Okay. And then okay, so if you, and this these properties, as you can also think of a problem that if you have a m, suppose m is the angular momentum and any component of angular momentum, and if you have a scalar quantity, so let me write scalar quantity means in something which invariant under rotation. So f r whatever it is, a scalar quantity, then their Poisson bracket also will be 0. Scalar quantity means invariant under rotation. See, this is a generator of rotation. Angular momentum is a generator of rotation, I think you know. of rotation. Angular momentum generates the rotation, and this is a constant under rotation. So this give you a very interesting feeling. And then you should know that the definition of canonical transformation in terms of Poisson bracket. So these are the all things you're supposed to know in Poisson bracket. And in the canonical transformation, another very important concept, canonical transformation, you're supposed to know first definition, then how to show definition through exact differentiation, then how to show a transformation is canonical. This and third is the how to find generating functional. For canonical, this is the most important. There are 4 type of generating functional, and how to find, you need to solve many problems to get this good. Then fourth thing is that application, I don't know, some application of canonical transformation, and then the canonical transformation in with respect to or with Poisson bracket. That particularly you should able to prove that fundamental Poisson brackets remains invariant under canonical transformation. If you learn these things, then your canonical transformation is over. Okay, anyhow, so at least because Dr. Kista is a new person to the department, so he may not know. I'll talk to him, and we'll in our section we'll finish syllabus nicely, no problem. If something is left, we'll and the remaining times, today is 13, so we have at least two class, 4, 5 classes. I think 4 classes definitely will get, and in 4 classes I'll able to finish your 2-body central force problem. So that will conclude your syllabus. And if you have any difficulties regarding this Hamiltonian and then Poisson bracket and then canonical transformation, or any topic you have some doubts, you can have some tutorial class or doubt clearing class to eliminate those. Okay, so let me give a brief introduction. Canonical transformation, all these things has taught, or any of the topics I mentioned has been taught or not?
Yes, sir, some of them have been taught.
Some of them has been taught is not a complete statement. No? If either all of state has been taught, or which topics are not taught, that. But anyhow, so this you have some knowledge about that, what you have to learn in this course. And now let me give you some introduction of 2-body central force. See, problem is that so far we were dealing with that a single particle or many point particle, and without their interaction, we have not considered their interaction. But suppose I have a problem, two particles, and they interact. It may be like a hydrogen atom. Hydrogen atom, there is the electron and proton. It is a bound state. So hydrogen atom itself a 2-body problem. Okay. So, but in physics, what happened that if you have two body, three body, or more bodies in the interaction, it is extremely difficult to solve. The two body problem, of course, I'm going to teach you that it can be solved, but only by reducing to a single body problem. So two body problem, if I want to write a Lagrangian, suppose if I want to write a Lagrangian for a two body. So there is a, say this particle is mass m1, this has particle mass m1 with respect to some reference frame. This particle coordinate is position vector is r1, this position vector is r2. Then I can write the Lagrangian half m r1 dot square. This is vectors dot square. Lagrangian is scalar. This is not a vector, but okay, you understand. Then half m2 r2 dot square. And then there will be some potential energy due to their interaction. So let us write that potential energy r1, r2. And only for a specific class of this potential, type of this potential, this problem can be solved. Not for all, and one of them is the central force. So central force, so when this potential u r1 r2 depends only on the separation of these two radial vector r, no angle dependence, only on r, which is r1 minus or r2 minus r1, r2 minus r1. And this magnitude of this r is vector is, but this r is the magnitude. So only the potential when depends on only the separation of these two potential and no angular dependence. Then we call this is a central force problem. Okay. So central force problem is only does not depend on angle. But first, what we'll do, we'll reduce this problem by going to center of mass frame. So let me draw what will be the center of mass. Suppose I have two body. This is body. This is your R1. This is your R2, and let us consider your center of mass is here, and then this coordinate is R. Suppose position vector. So immediately you can write, you all know that this r will be m1 r1 plus m2 r2 by m1 plus, by taking moments or whatever way you prove it, you can. So this is the center of mass coordinate r. And there also you can define the radial this relative coordinate r, which is r2 minus r1. So if this potential does not depend on it only depends on the r, then this equation can be reduced to a single one body problem with a reduced mass kind of thing. So that will this will discuss in next class, but maybe I'll prove it. But this you will get, supposed to get, if I substitute these two in this Lagrangian, then I'll get half m1, and then you have r1. So if you can solve for r1 and r2, then it will become like r minus m2 m1 plus m2 r vector dot whole square plus half m2 r vector, the center of mass coordinate m1 by m1 plus m2 r vector dot square, no, dot, then whole square, and minus u. It's supposed to be r and r, but since I said it depends only on r, it will be u r. So potential does not depend on the center of mass. And because of that, it will be easy to separate out, and we'll see there will be, I can think of this motion that the center of mass moving freely, and there is a relative motion with respect to center of mass. So first you derive this Lagrangian, come to this Lagrangian, you can very easily solve these two equations and substitute back in the Lagrangian, you will get this Lagrangian for, and then we'll simplify this Lagrangian after substitute. This Lagrangian, I expect it will be r, it will be small r, it will be r dot and r dot. So these terms is supposed to be in the final Lagrangian. So you just find this Lagrangian, and we'll continue from here in next week class. So this time is over, and also if you have any question, please let me know. Okay, so I'll stop recording.